There is a sound that soldiers on the ground recognize before they ever see the plane. A low, guttural roar that arrives before the silhouette appears on the horizon. And when it does appear, it looks like nothing you've seen before. It isn't elegant, it isn't sharp, it doesn't have the clean lines of a modern fighter. It has a flat nose, straight wings, two engines mounted on the rear like humps. And in the center of it all, peeking out from under the nose, the barrels of a cannon that spins at a speed the human eye cannot follow. It is called the A-10 Thunderbolt II. The soldiers who depended on it for survival call it the Warthog. And they don't call it that because of its looks. They call it that because it does exactly what a wild boar does when cornered. It takes the hit, it doesn't back down, and it keeps attacking. This aircraft was designed for something no modern fighter accepts doing. Going down, getting close to the enemy, taking fire, surviving the fire, and coming back for another pass. Today, you're going to see how something like this is made, because manufacturing an airplane that accepts being hit and keeps flying isn't conventional engineering. It's a completely different category of problem. It all started with a question the Pentagon was asking in the early 60s. How do you destroy a tank from the air reliably, accurately, and repeatedly in real combat conditions under anti-aircraft fire from the ground? Available fighters could drop missiles and bombs, but doing so with precision against small moving targets at low altitude with enemy fire coming up at you was a different story. They needed something else. The answer was the GAU-8/A Avenger, a 7-barrel rotary cannon, 30mm caliber, a rate of fire of up to 4,200 rounds per minute, capable of piercing the top armor of almost any armored vehicle of the era. The complete system, gun, ammo drum, and feed mechanism weighed about 1,800 kilograms. Nearly 2 tons of weaponry, and here's the decision that changed everything. Instead of taking an existing plane and mounting the gun on it, the AX program did the opposite. It designed the plane around the gun. The GAU-8/A occupies the entire nose of the A-10. Its axis of rotation is aligned with the aircraft's axis of symmetry so that the recoil, an average force of about 10,000 pounds during firing, doesn't generate a yaw moment. The nose landing gear is offset to the side to make room for the cannon. When the weapon is removed for maintenance, a jack must be placed under the plane's tail. Without the gun, the aircraft tips over backward. The plane doesn't have the gun. The plane is the gun. Everything else is subordinate to that fact. Most modern combat aircraft seek to reduce mass, minimize drag, and maximize high-speed performance. The A-10 took a different decision at almost every point of its design. The fuselage was built primarily with aluminum alloys, not carbon fiber composites, not titanium throughout the entire structure. Aluminum used with a very specific logic, a structure that deforms under impact without catastrophic failure, one that can be repaired in the field with basic tools, one that doesn't require specialized facilities to return the plane to service. The philosophy was explicit from day one. This plane is going to take fire. The design has to assume that and survive regardless. Fuselage panels are riveted, not bonded, accessible. Main parts are interchangeable between aircraft of the same fleet. Maintenance techs can replace a damaged panel in hours, not days. The A-10 was conceived to operate from forward bases, not depot maintenance facilities, meaning repairability had to be baked into the design from the start. The wings are straight, not swept, a decision that sacrifices top speed for low speed, low altitude maneuverability, exactly where the A-10 has to work. Straight wings generate more lift at low speeds, allow for tighter turns at altitudes where the margin for error is minimal, and offer 11 hardpoints for external weaponry. 16,000 pounds of external ordnance, missiles, guided bombs, rockets, targeting pods, all hanging from wings designed to fly slow and low. But the most iconic element of the entire structure isn't in the wings or the outer fuselage. It's in the center of the plane, surrounding the pilot. The so-called bathtub is a titanium capsule that completely envelops the pilot and critical flight systems. It's not a plate added for reinforcement, it is a structural element of the plane. It's part of the airframe. The pilot literally sits inside a titanium box. Titanium was chosen for a very specific reason. At an equivalent weight, it offers significantly higher penetration resistance than steel. And weight matters in an airplane. The bathtub can't be infinitely thick because every added kilogram is lost performance. The engineering of that capsule was a brutal exercise in optimization. How much titanium do you need in each zone to stop the fragments and projectiles the plane might encounter without adding more mass than strictly necessary? The result is a structure of varying thicknesses. Thicker where the threat is greatest, under the seat in front of the pilot, protecting control systems. Thinner where the probability of a critical hit is lower, and the bathtub doesn't just protect the pilot. Primary hydraulic lines in the most critical flight control systems also run inside or near that protection. Because in a plane designed to absorb damage, the question isn't if the pilot will take fire. The question is if he will be able to keep flying after taking it. The answer provided by the A-10's design was yes, as long as the fire doesn't breach the titanium. General Dynamics received the contract for the GAU-8/A in 1971. What they manufactured is still today one of the most brutal weapon systems ever integrated into a tactical aviation platform. 7 barrels, 30mm caliber, hydraulic rotation, selectable rate of fire between 2,100 and 4,200 rounds per minute. The complete system measures just over 5.5 meters long when mounted. The ammunition drum has a capacity for 1,174 rounds. The primary ammunition, the PGU-14/B armor-piercing round, has a depleted uranium core. This isn't by accident. Depleted uranium has a higher density than tungsten, the other standard material for armor penetration. Higher density means higher kinetic energy per unit of volume, more piercing power, and when that round hits armor, it doesn't just pierce. Depleted uranium has an additional property that makes it uniquely lethal. Instead of mushrooming upon impact, as tungsten does, it self-sharpens. The tip of the projectile breaks into particles that generate heat and secondary fragmentation inside the armored vehicle. Fabricating that gun involved solving problems that were unprecedented in tactical aviation. The average recoil during firing is about 10,000 pounds of force. For context, the thrust of each of the A-10's 2 TF-34 engines is approximately 9,000 pounds. Firing the gun at maximum rate generates a braking force that exceeds the thrust of an entire engine. If that force weren't perfectly aligned with the aircraft's axis of symmetry, the recoil would generate a torque that would make the aircraft uncontrollable. The solution was the precise alignment of the gun's axis with the aircraft's center of thrust, and the asymmetrical mounting of the ammunition drum to compensate for the shifting mass as rounds are spent. But the most unexpected problem appeared during testing. When the gun fired, the gases generated by the combustion of the propellant were sucked into the engine air intakes. And those gases, rich in carbon monoxide and incomplete combustion particles, choked the engines. Flame out. Both engines, simultaneously. In the first firing test, the plane was left without propulsion after every long burst. The solution was elegant in its simplicity. Automatically activate the engine igniters every time the gun starts firing. The igniters reignite the engines instantaneously if a gas-induced stall occurs. The pilot doesn't even notice. The burst ends, the engines keep running, the plane keeps flying. That detail, that real problem discovered in real tests, solved with real engineering, perfectly summarizes the philosophy of the A-10. It wasn't a plane born perfect on paper. It was a plane that became real by finding problems and solving them one by one. They aren't integrated into the wing root. They aren't hanging under the wings in conventional nacelles. They are mounted on the upper rear of the fuselage, one on each side of the vertical tail, high and far back. That position isn't an aesthetic whim. It's applied survival. First, high-mounted engines are protected by the fuselage structure from below. The anti-aircraft fire the A-10 will face comes mainly from the ground, at low angles or vertically upward. An engine mounted under the wing is much easier to hit than one protected by the plane's body from below. Second, the separation between the two engines is maximized. If a projectile hits one engine, the probability that the resulting fragments or explosion will reach the second engine is minimal. The A-10 can fly on a single engine, and it has returned to base on one engine more times than any official record fully captures. Third, the engine exhaust gases, which generate an infrared signature detectable by heat-seeking missiles, mix with the airflow from the tail before exiting. The temperature of the gas plume is lower and the infrared signature is reduced. The TF-34s aren't the most powerful or advanced engines. They are reliable, simple to maintain, and economical enough for a mission where what matters isn't top speed, but time on target. The A-10 can stay over the battlefield much longer than a supersonic fighter, because it consumes less fuel, and its engines don't require the high-performance maintenance conditions of advanced turbines. The A-10 has two completely independent hydraulic systems. It's not just backup redundancy. They are two parallel systems that share the load under normal conditions, and can take over individually if the other fails due to combat damage. The lines for each system run along physically separate routes inside the plane, so a single impact cannot sever both simultaneously. And if both hydraulic systems fail, there is a third level. The A-10 has manual reversion flight control. The most critical control surfaces, elevators and ailerons, can be operated directly via mechanical cables without depending on any power system. The pilot moves the controls. The controls move the surfaces. No electricity, no hydraulics. In modern aviation, that is almost archaeology. Most current combat planes are pure fly-by-wire. If the control systems fail, the plane doesn't fly. The A-10 has a mechanical reserve that allows the pilot to maintain control even under conditions of catastrophic system damage. The fuel tanks are also designed to survive. They are protected by explosion-suppressant foam on the inside. In the event of an impact, the foam absorbs spilled fuel and reduces the chance of ignition. The A-10 can take hits to the tanks and keep flying. This redundancy isn't free. It adds weight, it adds maintenance complexity, it reduces on-paper performance. But in the environment where the A-10 operates, low altitude, anti-aircraft fire, proximity to combat, that redundancy is the difference between coming home and not. The final assembly of the A-10 was different from any other combat aircraft of its generation. Not because it was more complex in terms of materials or electronic systems, but because the final validation didn't seek to prove the plane could fly fast or maneuver like a fighter. It sought to prove it could survive, keep functioning after damage, and return the pilot to base. The firing tests of the GAU-8/A with the complete aircraft were the moment of truth. The recoil, the gases, the flameout. Every problem discovered in testing was an opportunity to improve the system before a pilot's life depended on it in real combat. The complete aircraft, aluminum fuselage, titanium bathtub, 2 rear engines, GAU-8/A in the nose, 11 hardpoints, dual hydraulic systems, and mechanical backup, was subjected to controllability tests under simulated damage conditions. Flight with one engine. Flight with partially inoperative control surfaces. Flight with hydraulic system damage. In almost every case, the aircraft remained controllable. That survivability wasn't just a performance stat. It was the product of a complete engineering system where every decision, engine placement, fuselage material, the titanium bathtub, hydraulic redundancy, gun positioning, had been made with the same question in mind. Does it keep flying if it takes this hit? If the answer was yes, the design was correct. The A-10 entered service in 1976. And for years it was criticized. Too slow. Too vulnerable in contested airspace. In the era of long-range missiles and sophisticated air defense systems, what was a subsonic attack plane doing in the inventory of the world's most advanced air force? The answer came in January 1991. During Operation Desert Storm, A-10s destroyed more than 900 tanks, 2,000 motor vehicles, 1,200 artillery pieces, and an amount of war material that no other aircraft in the conflict matched individually. They returned to base with damage that would have been a total loss for any other plane. One of the most cited cases is an A-10 that returned with one engine destroyed, the landing gear inoperative, the primary hydraulic system failed, and more than 300 projectile hits in the airframe. It belly landed. The pilot survived. In Afghanistan and Iraq, the A-10 proved something else. That persistence over target, the ability to stay flying over the battlefield for hours, identifying threats, responding to calls from ground troops, making repeated passes, was a capability that supersonic fighters simply couldn't replicate the same way. Not because they didn't have the weapons, but because time on target has a fuel cost that the A-10 pays much more cheaply than any supersonic alternative. In February 2026, the U.S. Air Force confirmed the rollout of the last A-10 from the depot maintenance cycle at Hill AFB. The retirement is underway. The debate won't end soon. There are those who argue that the A-10 has no place in a high-intensity conflict against an adversary with modern air defense systems. That it is too slow, too visible, and too vulnerable in the kind of airspace it would face against China or Russia. They are partly right. But those who point out that most conflicts where American ground forces have needed close air support in the last 30 years haven't been high-intensity conflicts against advanced air defenses are also right. They have been Afghanistan, Iraq, Syria, environments where what a soldier on the ground needs isn't the fastest plane in the world, but the plane that can stay, identify the enemy feet away from their own positions, and fire with precision. And the question that remains without a clear answer is this. When the last A-10 lands for the final time, what platform can do the same? Not launch missiles from 100 miles away, not fly over at 40,000 feet, but get down, stay, absorb the punishment, and come back for another pass. The A-10 wasn't the most advanced plane of its era. It was the most honest plane of its era. Built with a single industrial and tactical obsession, survive long enough to fire again. And that obsession turned into titanium, aluminum, and 7 barrels spinning at impossible speeds was enough to earn a place in the history of combat aviation that no other aircraft has managed to replicate yet.